Okay, when we're talking about data bias, one important topic is data that's not representative. So we've got our familiar framework of 6 questions. And we want to ask each of those 6 questions here. So what's the description of this problem? Well, data is only useful insofar as it represents what it claims to represent. So there, depending on the situation, someone or some group could be overrepresented in a data set or underrepresented. Those are both possibilities and both potential problems. Of course, this is a story about the have and the have-nots, as it often is. And so, typically we're talking about some group being overrepresented in a data set that's not good for them to be overrepresented in, or vice versa. So the question is, how should we handle data that doesn't represent what it claims to represent? Or, maybe it doesn't make any claims, but we just need to think about what it should represent instead of what it does represent. All right, let's think about what's familiar about this problem. So if you've taken a statistics course, just a basic intro to statistics course, one of the topics is inferential statistics, okay? So inferential statistics is, you have an underlying population, and for whatever reason, it'd be impractical or impossible or difficult or whatever to get data about that entire population. So you take a subset or a sample of the population, you analyze it, and then you make a probabilistic projection back onto the population from the sample. Okay, so the sample has to represent the population, and if it doesn't, then the analysis of the sample isn't useful to project back on the population. So statisticians have known this for decades. It's called selection bias. If you've taken a statistics course, you might recognize this picture. So this is Harry Truman after winning the presidency, and what he's doing is holding up a newspaper that was printed the night before, because the prediction that the newspaper made was that Truman's rival was going to win, and so they printed up this paper as if the rival had won. Then they woke up the next day. It turned out Truman had won the election, and so Truman is having some fun with them by holding up this false newspaper, right? So the problem was that the survey, like it was a poll, and then you had the election, right? So the election, Truman won. The poll, Dewey supporters were overrepresented in the poll, and I think the claim is something like, it was a phone survey and Dewey supporters had, more access to phones or something like that. But anyways, it was an overrepresentation, and so the probabilistic projection back onto the population, the voters in this case, was inaccurate. Okay, so we have to think about that. That's what we used to. I mean, that's been talked about for decades. That's familiar. Okay. But what's new about this problem because of just the scale of digital technology? All right, well, so those best practices and those careful statistical controls were worked out on small data. And by small data, I mean there's not a super good definition. Maybe something like data that fits into a Microsoft Excel document or something like that. But in the age of big data, people oftentimes abandon or ignore, or maybe it's just impractical to pay attention to those statistical controls that have been developed, those best practices that we already have. Big data is more like there's a huge data source over here, there's a huge data source over here, there's a huge data source over here, and we just kind of dump them all together, and then we just make some sense of the data that we have. But those kinds of careful controls that work pretty well in inferential statistics. Obviously, I can't make a statement about every single person that uses data, but in my experience, those careful controls are not observed or practiced, and there's not a lot of accountability. So, big, big is obviously a relative term, relative to small. But one thing we could say that big does mean sometimes, unfortunately, is sloppy. Okay, so what's new about this problem, because not just of the scale, but of the capabilities of digital technology? Well, think about the accountability that the Dewey-Truman situation has, right? You had this immediate feedback, this immediate accountability that there's something wrong with the sample data, right? It told them, it took a test and it failed the test. And so you got this feedback that there was something wrong. So now we know that it's wrong. We just have to figure out why it's wrong. So they go back and they're like, what did we do? Did we depend too much on phones and phone use? And there's more Dewey supporters that have phones. And then they can investigate and figure out. Well, in artificial intelligence, data is not used to estimate population parameters. We're not making that probabilistic inference back onto the population. That's not why we have this sample, the subset of data. We have the data because we want to use it to create a model that can make predictions. So that's a different thing. That is not what the best practices in inferential statistics were developed to account for. Okay. So the particular problem is that the predictions that models make can become what I'm calling self-fulfilling prophecies. You've heard that phrase before, I'm sure. So the idea is that the model could have a bias that it got from having inaccurate or non-representative data, but the bias is like self-reinforcing because the predictions that it's make, people live up to them, and so you don't get that feedback, that accountability of, oh, there's something wrong with our model. Sometimes you do, not all the time. Okay, next question. Ethical values are relevant. That's a pretty easy one in this case. Bias and fairness are enemies. If you have a lot of bias, that creates unfairness. And so that is the value that's on the line here. So first, let me give you a famous example. And this is an example where we do get feedback. And that's one of the reasons it's such a famous example. So a researcher named Joy Bolawimi, she's does a lot of important research, but the easiest way to access a summary of her research is a show on Netflix, a documentary called The Coded Gaze. So what she's doing is she's doing research using facial recognition technology. And it turns out that the facial recognition technology wasn't recognizing her face. And at first she didn't think anything of it. But then she figured out that it's because her skin tone is darker. So, oops, that's a bias problem. How did that happen? Where did it come from? Well, I mean, I have heard analyses that's like something about the reflection of the light that they're using, but that explanation doesn't strike me as very convincing. For one thing, in her work, she shows that it's not only race. It's also the more male and the more white a face is, the better facial recognition technologies, and this is across systems, do at recognizing those faces. Okay, so if it's a light refraction kind of thing, that wouldn't have anything to do with the maleness or femaleness of the face. So what is the more likely explanation? Well, it's that training data was used, and so this system was fed all these images, and it learned how to detect faces. And it must have been true that the faces that the system learned on, were overwhelmingly white and male. That's why it got so good at recognizing those faces. And then when it sees a face that's less male or less white than it's used to, the system gets confused. This is an example of, facial recognition technology is supposed to be a promise that it recognizes faces. So it should recognize all faces, but it doesn't. Here's an example, that example is where you do get that feedback loop, right? Because Bolawimi was able to, find out real fast that the system didn't work on her face. So at least you had an alarm bell, right? That we can go back and say, this is no good. We got to fix this. There's other cases, though, and I do think these are going to be more common where you don't get a feedback loop. So, one thing that, one area that data is being used a lot is in policing. And that's because crime happens in patterns. And so that seems to be a really nice way to use data to be able to make predictions. And so the idea is that, resources are not infinite. So the police don't have an infinite amount of, they can't just send everybody everywhere. So they have to it makes more sense, right, to use resources where the crime is going to happen if you can accurately predict that. Well, what happens is, the story starts with discretion. So police have a lot of discretion about who they're going to stop and who they're going to search and where they're going to look. And if they're looking in areas that are, for example, poorer, which is a lot of times what happens, they're going to find more crimes just because they're looking more. Well, then that tells the data tells the system, hey, in this area you've got more crime, and so it justifies sending more resources to that area because the system is telling us that there's more crimes in this area. Well, now we have more resources and we have more police resources concentrated in this area, and guess what? Now they find more things because they're looking harder in this area. So this is what I meant before when I talked about a self-fulfilling prophecy, or this is a pretty good example of a self-fulfilling prophecy. Because the system made the prediction, that seems to validate the prediction. But there's bias at the heart of this. Okay, so what are the potential solutions? Are there any? In this case, I actually am more optimistic that I think this is a problem that we can address. As I've pointed out before, fortunately, in statistics, there are a lot of best practices and statistical controls about how to deal with this. The key is, though, that we need to actually be aware that there's a bias problem, and when there's no feedback, we might not be aware. And also, we need to care. We need to say, hey, this is a problem. We don't want this to be happening, and this is happening. All right, that is the problem of non-representative data.